All right, let's see. Is my stream back on? Hopefully just restarting OBS fixes this. Yeah, it's good now. Okay. We'll just do one quick verify, look at my phone. Maybe. Yeah, it's good. Okay, yeah, it looks good. All right, hopefully, I don't know if it started bad and lagged. I don't know how it got desynced, but we will roll from here. Okay, so we are looking at level 11. The thing we were going to investigate was, I guess, how to use pwn tools with these later toddler 2 levels. Yeah, so let's go ahead and let's create this x2.py, Python x2.py, and let's edit it from outside of the VM just so it's a little bit easier. Okay, so if we import pwn context updates, who knows what we're going to need? Probably not that, but whatever. Encoding equals Latin. Log level equals, we'll just pass the bug on the command line if we would want that. And then let's do with pwn process of this as target. And then we'll do target clean, pwn info, decode that. Okay, maybe we'll clean for a full second just because we're operating in the VM and things, I don't know, I'd be surprised if a normal clean didn't work, but we'll give it a full second to read that just to be safe. Actually, just, I'm kind of curious. I don't think it's going to fail. Let's just do that. We'll notice if it does. And then let's do with pwn remotes localhost 1337 as remote. And we'll do pwn info remotes clean decode. And let's just start with that. Okay, so if we run this script, okay, we can see all of this allowing syscall stuff, and then we can see when we connect up, it tells us the thing that it tells us when we connect up, basically all of our commands. And then what we might want to do is create a program, load the program, and then output the program. So if we do pwn send create program 0, load program 0, and you're going to see what happens if I do this. So I don't know exactly how you're running it, but if I do load program, and let's just say I pass it like an A, like I'm about to just load a single byte program A or something, and then we do output program 0, and then let's just do a quit operation as well. And let's do that. And then if we do pwn, well, not pwn send, we want remote send. And then remote read all pwn info decode. Okay. Oh, I needed an index. Good call. Load program 0A. Okay, let's run this again. Okay. So the first thing we're going to notice is that this is just hanging forever. So is this how you were trying to demonstrate, I guess, to yourself that you could just do basic interactions using pwn tools? Did you have something that looked like basically exactly like this? I guess the other thing we could try, and it could make a difference. I'm trying to think. Yeah, this has the potential to make a difference if you did this instead. You do this, and this is actually what I'm doing here is different, even though it's going to look basically the same. Load program 0a, and you use sendline, but did you do everything all concatenated in one string? Output program 0 and quit. So you had something that looked like this, right? Exactly. Okay. So this, I think, has the potential to work, but can also fail. And I'm not sure what the distribution of succeeding versus failing looks like. There's a chance it'll just end up always succeeding, or there's a chance it'll end up just always failing. There's a chance that it's somewhere in the middle, that sometimes it succeeds, sometimes it fails. Let's see what happens if we run it once. Okay, it looks like this failed. It has the exact same issue as before, which is that it's just hanging. And the issue of what's happening is that the very first thing that our target is doing is it's calling scanf, like, I don't know, we'd have to look at the IDA, but something like this or something. And when it does that, the first thing when we send all this data is it's going to detect this create program, and then the space, we'll just do that. It catches all of this, and that's how the scanf terminates. And then it'll call scanf again. I believe it looks like this. It might straight read in a number. I think it calls A2I, though. I'm not 100% sure. And then it's going to detect this 0 new line. And then it's going to call scanf again. And it's going to read in this load program 0. No, just load program. And then it's going to scanf again, and it's going to read in 0 space. Notice how basically all of these are ending on white space characters, whether that's a space or a new line character. That's kind of how this scanf is ending itself. Otherwise, it could go up to 127. Okay, but finally, this is where it differs. So now that we're doing a load program, what it's going to call is it's going to call read socket fd 256 buffer, basically. And what's going to happen here, what it's going to end up reading in, is it's going to read in all of this. It's going to read in, basically, it's going to attempt to read 256 bytes. And if we pretend that, like, maybe all of this gets sent before the program actually manages to do any amount of processing on it, as like a simple example, obviously it could be interleaved in arbitrary ways. If we imagine, though, that it all sent at once, which definitely happens in this case, all of this would be sent at once, then what's going to happen is all of this is going to get read in together. So it's going to read in all of this. Am I missing a new line? That. All of this gets read in, and that's why it hangs forever, because the quit operation never happens, which means we can't do a read all because technically the program's still... Well, I guess then what's going to happen after this is we're going to go back to the scanf 127s, and we're going to be looking for our next operation. So this is what's happening, and this is where we're hanging on, because the quit never actually got processed. Okay, so there's a question. Will sendline after make a difference on or doing receive untils to make sure the previous data is processed? Okay, so that's actually a good question. In a lot of challenges, we will acknowledge your command, and then you could do send afters or receive untils, and that would totally work. This challenge, though, if we... How do I want to show this? Let me VM connect on another thing. Let's run the challenge, and then let's netcat in. If we do this, what's going to happen is if we do, like, for instance, create program 0 and hit enter, this successfully just happened. We created the program, but we've got no acknowledgement back. So you can't do send line afters or receive untils because there's nothing to receive until to know that this is done processing. And we do that to make the race condition a bit easier because, you know, we don't want arbitrary syscall or extra syscalls happening in between. It makes it, I mean, still solvable. It just makes it unnecessarily more complicated. So it's actually easier that we don't acknowledge you, though, of course, it has these caveats that we're talking about here. Okay, so if we go back, Emacs x2, close that. Okay. All right, so it's weird that this didn't matter in 10, though. It doesn't acknowledge your commands here. So I don't think 10 acknowledged your commands. I mean, I guess you're saying that this works in 10. I guess is what you're saying. Let me see if sometimes it works. Let me run it like 3 times. Because I believe 10 will have this exact same structure to it. In terms of why it would end up failing. Now, there's a chance that the semaphores might introduce enough delay to where things won't be an issue, because I believe there's a semaphore on the load program. Is there? I think there is. There must be. Yeah, load program must have a semaphore with it. So it's possible that that semaphore, like, interaction makes it so that, I don't know, maybe it changes how this works. Oh no, but now we have the semaphore. So that would be, it's possible that the semaphore makes a difference. Okay, so we can see it hangs here. I'm just going to assume it's generally hanging. Let's actually look at level 10. I'm kind of curious if I run this in 10, if it's going to have the same issue. It is definitely possible the semaphores could make this different. VM connect Emacs x2.py. And let's run this. Python x2.py. It's actually interesting if this does work in 10. Huh. We're gonna fix the script. It looks like it's failing here in 10 as well. Now maybe sometimes it succeeds, there's more likely to succeed. Not super sure. Yeah, it looks like this is failing in 10 as well. So the simple solution, though, to this problem is basically if you want to load in a program, load a full 256 bytes. So what that would look like is, I'm trying to think if white space characters matter. I think it's fine if we have an extra white space character when we go into the next scanf. So what all you could do, for instance, is just do this plus, we'll say plus program. Maybe you want to assume that for some reason your program you want actually to use bytes, so we'll set up for bytes, and we can say like, hey, our program is BA times 256. So a 256 byte program, because what it's doing is a 256 byte read. Yeah. So now if we run this, we're going to see that it won't just hang. Yeah, we'll see. And it outputs the 256As. So I don't think there's I'm trying to think if there's any reason why you wouldn't be okay with sending a full 256 bytes. Can't think of any reason why you would like really prefer to send just a single byte rather than send a full 256. Maybe there's a reason, but I would say just send a full 256 bytes for your program if you're going to load a program. And then you won't have to deal with these issues. And again, you also don't have to do this now. You could go to this instead, and this will also work. So if we do this, and we'll do like, we'll do something like this plus program plus. Of course, we have to make sure that we're adding strings together, we're adding strings together. If we're adding bytes together, we're adding bytes together. We don't mix them, otherwise Python's going to yell at us. And the reason, just in case anyone's wondering, that the reason we're opting to use bytes here for demonstrating it, it doesn't really matter in this case, but you could imagine that maybe your program you wanted to be like 01 XFF FE, you know, arbitrary stuff, and you don't want UTF-8 messing you up, so just work with bytes. Okay. Though there's a chance maybe you don't need to because of this encoding equals Latin. I'm not 100% sure though. Either way, it's simpler to just use bytes if you're interested in doing non-ASCII data. Okay, so, and again, yeah, we can see that this works. Yeah, so the question is, so I need to pad my programs up to 256 bytes? Yeah, I would definitely recommend doing that. It's interesting that you didn't have that problem in 10. I'm imagining that there's a chance that if you were solving 10 and maybe you didn't test like the sort of base case scenario and just went straight into like an exploit, that if, for instance, you were doing a bunch of load programs in a row, that you would just end up having programs that have the string load program in it, and like eventually it would like desync itself and resync itself and desync itself and resync itself. And I can imagine a scenario where you're spamming load program in it and not sending 256 byte programs, and it does actually work out through desyncing and resyncing and stuff. It would be a little wild, but it could actually work out. But I would definitely recommend just using 256 byte programs. Okay. Did you have any more questions on 11? I can't get too specific on 11 since, you know, it's kind of approaching the final boss territory here, but I could at least answer high-level questions if you have any. Okay, and otherwise, what other questions are there? So there was a question, I think, about baby jail 10. There's also, I see a question about baby mem 7.1. Okay, let's start with talking about baby jail 10. And if the person that had a question about baby jail 10 had any specific questions, that would make talking about it a little bit easier. But I guess I can at least talk about it at a high level otherwise. Baby jail sandboxing. Baby jail 10. Yes, level 11, as you pointed out, introduces a semaphore, which, you know, semaphores are the death of race conditions. It's great. Or are they? Okay, so we are loading up baby jail 10. Clear. Let's see what this says. Okay, so we want, it was baby jail 10, yeah. I am getting garbage when I tried to leak flag as exit's first argument. Okay. I'm gonna have to refresh myself with this. So we've taken a path. It says shellcode do whatever you want, though I think it's probably gonna seccomp us because we're in jail. And I think that's most of the levels is seccomp. Well, I guess the first half is chroot, second half is seccomp. Okay, let's just pass flag. We're gonna see that's, oh, it doesn't fail. Okay, it's fine to do flag, but then the challenge here only allow, does it not tell us right away what they are? Did I launch, why does it not tell us our seccomp filter early? Guess we report it when we load it. We're currently reading. Yeah, I guess it makes sense. It's not the end of the world. Kind of nice if it told us right away, but we will roll with it. Okay, let's send P for a nice push RAX. I don't know if anyone's bothered to memorize some ASCII x86 instructions, but good one to keep in mind is P is push RAX. It's a lot of fun. Obviously, you know stuff like CC is an int3, but you can't type CC with your keyboard very easily. You can type P, it's push. It's great. Okay. So allowing syscall, read, and exit. So that means we just opened up the flag. Kind of nice if we said the file descriptor we opened it on. Not a huge challenge, but maybe it would be nice. So we open the file descriptor. We don't have a limit, I don't think, on baby jail level 10 on how long our shellcode can be. I think that's a baby shell sort of thing to impose limits on the length of shellcode. So this only, basically all we can do is do read syscalls, which we can imagine, that's great, we can read in the flag that we just opened, but we can't write it out to ourselves, which is not great. But fortunately, and there's some reason we're very generously offering this exit syscall, you know, maybe we can start side channeling stuff. So if we look at man to exit, this is going to tell us all about the exit syscall. And what it's going to tell us is lots of text. Terminates the calling process immediately, blah, 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 process closed, any children, blah, blah, blah. Oh, this is fun information. I didn't realize this is where it documented this. The process are inherited by init. Yeah, this is where this crazy stuff happens. True, doesn't matter for us. Okay, here we go. The value status and 0xff is returned to the parent process as the process's exit status and can be collected using one of the wait family of calls. Okay, let's demonstrate that. If we do, let's just run things from IPython. We do import pwn context arch, pwn context update. Here we definitely care about arch, AMD64, and we'll just do encoding for fun. I don't know if we'll need it, but Latin, let's just roll with that. And then let's do with pwn process challenge, baby jail level 10. Oh, and we have source code on this, don't we? I forgot about that. Okay, cool. So we could read more about it if we wanted to, but probably we have a general idea of what's going on here. And as a quick sanity check to make sure that we're setting up a script well, let's just do target clean pwn info this decode that. Okay, and we need also an argv1, which looks like /flag is totally fine for us to open that. So let's do that. And let's just run this. Okay, so we can see, tells us all of our introductory stuff. Looking for some shellcode. So let's use, yeah, I guess at this point in baby jail, it's totally fine to just keep it easy for ourselves and just use shellcraft. course, if shellcraft fails, you better be ready to start writing shellcode. And in general, it's definitely a good idea to learn how to write shellcode. We're just using shellcraft because we understand shellcode, and shellcraft just makes it easier. So we can type less, basically. Shellcraft exit, and let's just do 42. Let's make sure this gives us some assembly that we want. Yep, okay, so we can see this is the shellcode that we're about to generate. So push 0x2a, pop that into RDI, the first argument to our syscall. We push 0x3c, we pop that into RAX, and we perform our syscall. So let's do shellcode equals that. We'll do that again. And then let's do target.send pwn.asm shellcode. And then we'll just read everything again. I guess instead of clean, let's just do read all. Make sure we read everything remaining in the process. And then the thing that we're interested in is the exit code, which we can get from pwn tools by doing target.status. Well, we're in IPython. We'll guess what it is after this. Okay, so it executed our shellcode. I mean, I guess immediately we can see that pwn tools told us that we stopped with exit code 42. But alternatively, is it .exit code? Is it no underscore? Swear everything does this differently. Well, I guess we can tab complete. Target. Can we tab complete? Or what just happened? Oh my. Something is going crazy. I must have hit tab enter. Why are we... Okay. Why is tab completion just failing? And why is this happening? I'm so confused. Reset. Target. Tab. Okay, tab is just dead. Am I in the VM? Don't think so. VM logs. Nothing popping up, so I don't think I started a VM. Okay. Is it because I'm so zoomed in? I don't know. Let's just do dir target. Read the docs. Status. Exit. No. Why am I having such a hard time getting the exit code? Pull. Pull will definitely do it. Is there not a way to just straight up get it though? I thought there was like .exit code. Maybe we can only pull. Status. Huh. Could have sworn there was a way to get it without calling pull. But it would seem no. Okay, so if we do target pull, and if we pass true to make sure it blocks until the process actually exits, that'll give us our exit code. So anyways, back to all of this. If we now do pwn info, and let's just do exit code, and we'll do exit code equals target pull blocking exit code there. Okay, so just to confirm, we can pull that out. We don't have to just read this helpful information from pwn tools. We can actually programmatically grab it. Okay, so next. So that shows that we can use exit to send data in some way, right? We don't have the ability to use the write syscall, but apparently we can use this exit syscall to at least send a byte of data. And if you can send a byte of data, or even more simply, which we'll see in, I guess, later levels of this module, if you can send a bit of data at a time, you can send arbitrary amounts of data now, right? If you can just repeatedly send out whatever your data is a bit at a time, you're good to go. Okay, so let's, I guess, show what we could do to add a little bit more to our shellcode. So if instead of exiting on 42, if instead we do, let's say, pwn shellcraft read, and we're going to be taking in a file descriptor, a buffer, and then a count. So if we read from file descriptor 3, which if we imagine file descriptor 0, 1, 2 are the standard in, standard out, standard error, and assuming that this program didn't open something else up, the next in line thing is 3, and also that it didn't close standard in, standard out, standard error. Next in line is 3. We could verify that with strace if we're wrong. And then let's do, I think we can say like this if we want to just read to the stack. And let's say we want to read, let's just read 1 byte. And I'll leave it as I'll let you figure out how you can read the rest, right? This is going to show this off though. Okay, if we now do pwn shellcraft exit, and it's possible that we might want to actually just write some assembly here. I mean, we can use a little bit of shellcraft and some assembly. Let's do that. If we do an f multi-line string, we put this in curly braces, and then this in curly braces. And what we want to do is we want to exit with, let's say, exit with RDI. And what we want RDI to be is, let's do move DIL, so 1 single byte from RSP. And I think this will work. It's possible we have to say like byte pointer here. I think it'll work without though. We'll try it with both. So that's our shellcode now. Let's see. Okay, so we can see we have a different exit code rather than that 42, so something happened here. Okay, and if we do CHR of 112, we're going to see it's a P, so the very first letter of the flag. And there it is. Okay. And just since I'm curious, I think we can do this without byte pointer because this basically says how much data we want to read, because that has a size associated with it. Yeah, it works just fine. Of course, when it disassembles it, it just, standardizes. It says byte pointer, but okay. Hopefully this answers or gets you well on your way to attempting BabyJail level 10. And you'll have to think, I guess, a little bit about how you'd get the next byte and the byte after that, etc. But hopefully it's not too difficult. At this point, it's just an exercise in assembly. All right, so that is level 10 of BabyJail. What else did we have? Saw, I think, a baby mem question. And I guess I'm seeing also a question about baby shellcode 10. Let's do that baby mem first. I guess I'm making sure real quick that there's not any follow-on questions to toddler 2 stuff. Yeah, I'm not seeing any. Okay. So baby mem 7.1. Fastest way to get the padding between the input buffer and the return address. Padding between the input buffer and the return address. Okay, yeah, that's a very good question. Baby mem 7.1. Memory errors. 7.1, practice. Okay, so if we run the challenge, let's just run it so we have some idea how we ran 7.1. Let's just run 7.0 real quick. But we'll demonstrate this on 7.1 because I think 7.0 is going to give us basically that information for us. Yeah, okay. So we have stack, and this just prints paragraphs and paragraphs of text. Canary is disabled. Okay, that's cool. Could have used checksec to verify that. Okay. Okay, so this binary is position independent. Again, we could use checksec to confirm that. You cannot know exactly where the winAuth function is. So I guess a quick, easy thing to test is if we just spam out a bunch of A's, are we going to segfault? And I think the answer is almost certainly yes. Okay, it is. All right, that's all we needed to know then for answering that question about BabyMem 7.1. Let's switch back to 7.1 because probably what you're thinking is in 7.0 I can use all this helpful output information to figure this out. In reality, the goal of this helpful output information is to help you get the ground truth information immediately and then also be able to use Gdb to confirm that you can use Gdb to get this ground truth information for yourself. But I've noticed a lot of people don't exactly use the teaching information in that way, which I mean, I guess is fine. But that's what I would, in general, recommend if you know you're stuck on one of these things on your own and you're, yeah, I mean, the idea is that we have these teaching challenges that provide all this helpful information, but in theory, all of this information is totally recoverable with Gdb, and you could confirm that you're getting that information correctly using the teaching challenges. Okay, but anyways, how do we get the distance between, what was the question again? Guessing it's the distance between our buffer and the buffer and saved RIP. Let's see. Padding between the input buffer and the return address. Okay, yeah. So it is actually a little bit trickier than we probably want, but not too bad. Basically, I think we are going to end up going through an extra layer of dereferencing. But from a reverse engineering perspective, we can actually kind of just ignore that entirely if we break in Gdb at exactly the right point. Okay, so we're launching the program up in Gdb. We're going to do start. And then what we're going to do is we're going to disassemble main, which is going to have a bunch of stuff. Somewhere it's going to call read. Oh, wait, there's a challenge function. That is probably what we actually care about, is the challenge function. Okay, somewhere it's going to call read. Hopefully it's just once, otherwise we'll have to figure out which read we care about. Okay, so this is read. This is the only read as well. So this read right here is going to be when we sent all those A's, for example, and it segfaulted, this is the read syscall, or the read wrapper that goes eventually to the syscall that's pulling all that data in. And if we think back to our man pages about syscalls, we know that read takes 3 arguments. It takes RDI, or in this case, it's just using EDI, same thing, effectively, which is the file descriptor, which it's passing in here as 0, which means basically, hey, I want to read in from standard in. That's what this line is saying. And then we have RSI, which is the next argument. And RSI is where are we going to read this data to? And then the third argument is going to be this RDX, which is, I'm trying to think here. We look at syscall.sh x64. Not the third is, it's the fourth one that changes between syscalls and non-syscalls. RDX, good to go. Don't need to talk about that then. RDX is our third argument, and that's how many bytes we're going to read in. Okay, so let's go ahead and just break straight at this address, or we'll break at this offset from challenge just to make our solution a little more generic. So if we break at challenge plus 2 to 8, and then we continue. So it's asking us for a payload size. So let's just say 1,000. And then it is going to, we're going to be broken here. So we can see x8i RIP, currently at this read syscall we were talking about. And if we print RDI, the first argument, we can see it's that 0 we talked about, that's standard in. If we print RSI, this is where we're going to be reading to. So just straight into this address and data beyond that, depending on how many bytes. And the number of bytes is RDX. So, and if we, instead of printing this as hex, if we print this as decimal, we will see that is the 1,000 that we passed in. Okay. So this is where data is being read into. And then the next question is, where is our saved instruction pointer? And our saved instruction pointer is going to be at, effectively it's going to be at RBP plus 8. So if we look at, let's say, X2GX RBP. So if we think back to calling conventions within our program, we have our RBP, our RBP, which is our stack base pointer basically, and RSP, which is kind of where the top of the stack is, bottom of the stack. It depends on which direction you're thinking of the stack going, but you know, the furthest out point on the stack, and then RBP is the base of this function frame. And if you're confused about that, I think we have videos that talk about that. Hopefully, I'm pretty sure we do somewhere. Okay. But at RBP, we're saving two things. So at RBP, we have our saved base pointer. And so that means when we run to this challenge function and then return back, we're going to be returning back to main, and main needs to be able to restore its RBP. So at RBP contains the saved RBP, and then at RBP plus 8 contains the saved instruction pointer. So basically when we return back to main, which called challenge, we need to know where we're going to continue executing from. That gets saved to the stack. That is our saved RIP. That is stored at RBP plus 8. So right here. Okay, so if we want to overwrite this then, we need to know the distance basically between this and this. So if we do, and of course this is our saved instruction pointer. Where we really care about is where that is stored at. So where that's stored at is RBP plus 8. So right here is where it is stored. And if we print RBP plus 8 minus this RSI location, we are going to see the offset to where basically if we read in hex 78As, the next byte is going to start overwriting the saved instruction pointer. So this is how we can compute that. If we want to just confirm that everything we're saying isn't insane and that it actually is true, go ahead and try that. We'll just do quickly 0, or we'll do A times 0x78. Copy that. And we'll do, I guess we'll do it again in GDB. Let's do, do we have that saved? We do not. Start. Let's do disassess challenge. We'll break here again. Will be generic, could do either one, but challenge plus that. Is that hex? No, that's decimal. And if we continue, we'll say 1,000 again. And I guess where we're ultimately going to want to end up is, actually let's set a breakpoint here as well, right after, wait, where did I just set that breakpoint? 228, yeah, right here. Let's set one also right here, right after. So let's do break challenge plus 233, double plus. Let's continue. Okay, so if we send it this hex 78 amount of A's, and then we'll send it ZZ, and then we're going to hit enter, which is also going to be sending a new line character. Okay, and now if we look at X, how do we want to do this? We look at XGX RSI, which is basically where we started reading data in, right? Our RSI is where we're going to start reading data in. And if we just print out a bunch of these, we can see here is all of our A's being read in. Bunch of A's, bunch of A's, bunch of A's. Maybe it'll be even easier to see it if we do 100 BX instead of GX, single bytes at a time. We'll need, let's say, 200, bunch of A's, and then eventually it stops being A's. Probably 5A is a Z. Probably shouldn't have used Z since I don't know Z off the top of my head, but we can confirm that. 0x5A. Z. So here is that first Z, the second Z, and as I said, there's a new line character, so there's 0A. So if we do ord of a new line character, hex, right, that is 0A. So that is basically these three characters. And now if we look at, just to really hone in on what we overwrote in relation to the saved instruction pointer, if we do our x/gx, and then we specify RBP plus 8, we can see now that we have, of course, this is a little endian integer, which means we're overwriting the least significant bytes first. So we have a Z, and then a new line character. So we just overwrote the saved instruction pointer. And if we disassemble again, and let's go all the way to here, and let's continue. So we're just about to ret. If we look at the top of the stack, you can see exactly what we're talking about. So this is about to become where we're executing code at. And if we step, oh, well, we didn't crash, because if we would have overwritten the whole thing, we probably would have had an address that wasn't mapped. Apparently this address is in fact mapped, which is a little unfortunate because I wanted to show it segfault, but something's probably about to crash anyways. Oh, interesting. Now I'm confused. Why didn't it crash right away? Is GDB doing something that's preventing us from immediately crashing? We step one more time, we'll see we crashed at this address, because this address in fact is not mapped in. Okay, hopefully that is a super in-depth walkthrough kind of how you calculate that offset. Okay, what other questions? So I remember there was a question about baby shell level 10, I think. Color 2, level 10, yep, that stuff. Okay, so there's a question about toddler 1 level 11. Is toddler 1 level 11 the last level? Toddler 1. This. I see. Oh, yeah, okay, so this is the JIT program. Syscall closed. I think we have a lecture on this that if you haven't watched, I would highly recommend watching. And since this is the last level of the yellow belt, I will not really discuss it too much. But if you have not watched this video, it'd be incredibly useful to watch it. And then I guess the other thing I would say is that in previous office hours, I talked about this idea of like a zeroth order memory corruption, which is kind of like we read some data in and immediately we're overwriting like a function pointer or a saved instruction pointer or something like that. This level is, it's a little bit harder. It's the last level of yellow belt. So it's not a 0th order memory corruption. If you're thinking along the lines of achieving code execution in level 11, first of all, watch this video. And second of all, really hone in on this idea of, code execution, being able to hijack code execution is all about being able to ultimately overwrite a function pointer or something that controls where code is going. So focus, I guess, your attention on that. So maybe you can't directly overwrite a saved instruction pointer to do that, but maybe there are function pointers or something like a function pointer that, if you could overwrite it with arbitrary data, maybe you could start hijacking control flow execution. Okay, and then so just going through the chat, where was that question about baby shell level 10? Yeah, there. Okay, baby shell code 10. It's time to go over it. Okay, that's the sorting challenge, I guess. Okay, so baby shell code injection level 10. Yep, 10. Okay, let's start that, and then I'm also going to look at the rest of the chat. Go over read-only / write-only pipes. Embryo IO93. Yeah, I can talk about that as well. Okay, let's go over this first, and then I will look at embryo IO93 and talk about pipes. Okay, so level 10 is, according to the question, a level where we sort shellcode. So if we run this level, we can see, what can we see? Okay, I guess this is probably what tells us in all the levels. Okay, this will sanitize. Okay, this probably happens in all the levels. Okay, let's just send in our push rex instruction, executing filter, which tells us it just sorted your shellcode using bubble sort. Keep in mind the impact of memory endianness on this sort. E.g., the least significant byte being the rightmost byte. Okay, so it tells us more specifically how it's sorting it. So it's sorting with bubble sort. I guess the algorithm doesn't really matter. We don't really care about the algorithmic complexity, of how fast it sorted it. Just the fact that it's sorted it is what matters. But in order to sort something, you need to know kind of how are you sorting it, how are you treating the data, and the way that we're treating this data, if we look at it kind of like raw bytes, so we're taking 8 bytes at a time. We're treating this as 64-bit integers, and whatever is smaller ends up on the left, larger ends up on the right. We're sorting numbers. It's great. I guess just to test that a little bit more, if for instance we send in 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Failed to disassemble, but the bytes are this. Okay, so we can see we have our A's, we have our B's, and then we have this new line thing. Alternatively, if we send that backwards, so if we send the B's and then the A's, okay, that did not copy. Copy. Okay, it's just not copying. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Enter. We're going to see. Oh, wait, what? Executing. Why does this not look sorted? Eight, 4, 5, 6, 7, 8. Huh. Is it sorting it or not? I'm confused. Why is this not? All right, let's switch over to Pwn Tools and let's just try sending it like a generic send us the flag shellcode, and we should see that fail. It's treating it as 8 bytes at a time. Should be able to sort those numbers. Okay, if we do, let's just copy from this. I guess this was from Baby Jail. We were demoing that. We don't really care about all of this stuff. Okay, but this is going to send our shellcode. This is going to read. And let's just use shellcraft real quick to test this out. So if we do pwn shellcraft open open /flag like that, and we'll read 3 RSP 256, and then we'll write 1 RSP 256. Good enough. Realistically, we could use the result from this, basically how many bytes we read in. We'll just send 256 bytes. Why not? Okay. Then we'll exit 42. Let's see what happens. Do this. Need to change this real quick. Baby jail level 10. No, baby shell level 10. Okay, let's send this. So we sent this. This is a bunch of shellcode. It's a little bit tricky to see this sorting. We can immediately see that this doesn't look like our shellcode because we have like this out instruction. If we think about the shellcode we just wrote or used shellcraft to write, we'd never had an out instruction. Because why would we use the out instruction? And then there's going to be like crazy things. Basically, our shellcode's being changed. I'm slightly... Okay, hold on. Let's... Before we go down this too much, let's see... What if we use like this instruction? Move abs rax this. Okay, so this is more than 8 bytes. 3, 4, 5, 6, 7, 8. Yeah, so let's move like EAX. Okay, so let's just ditch all of this shellcode. Because we just wanted to show that, hey, our shellcode is in fact being changed. Let's instead do move EAX 0x1234. And then let's see how long that instruction is. So we can see that this is taking up 5 bytes. So let's maybe pad that with 3 nops just to get it to our full 8 bytes. We'll just do this. Okay, so now we have this, and we can see that this is not being modified because we've stayed under 8 bytes in this case. But if we do... we duplicate this, and instead of 1, 2, 3, 4, let's do 5, 6, 7, 8. Okay, so we can see this is how it's sorted. But if we, okay, so we have this with 1, 2, 3, 4, this with 5, 6, 7, 8. if we send this now in the opposite direction, 5, 6, 7, 8, 1, 2, 3, 4. I'm so confused. Why is it like seemingly not sorting our shellcode? Something here is wrong. Okay, let's look at this with GDB real quick. Let's do pwn Gdb Attach Target. Okay, and this is going to fail because we're not in tmux, but we can end this. Actually, let's make sure we have that. Let's run it again. Run history so we can just copy this to our clipboard, make sure we have this, because I'm about to do sudo tmux. Which means it's not going to be in my history. So sudo tmux ipython, paste this in. Here we go. Okay, so we are now attached to the process before we send our data. And okay, where? Okay, so we're gonna be executing here. So let's just go ahead and break there. Let's continue now. What? Was it not mapped yet? Gotta write this slightly differently. Make sure so we can break. Okay, hold on. Let me also just copy this. I feel like I'm going down a bit of a tangent, but very curious why this doesn't seem to be telling us that our shellcode is being sorted. We will do gdb script equals this. Okay, so we're going to break here. We're going to attach. We're going to break. Okay. I'm trying to think of the order that this is all happening in. I guess we can check the source code because we're on baby shell. Okay, so the sorting stuff happens. Print the disassembly. Input equals shellcode mem. Execute shellcode mem. Read. We're definitely reading into shellcode mem. Why is my breakpoint not being hit? Oh, is it because the read is overwriting the CC byte that GDB is adding? Probably. So basically, I think what's happening why my GDB breakpoint is failing is the way that GDB works is it's going to end up inserting a CC byte, an int3 instruction, straight at wherever your breakpoint is and keeps track of what data was there so that it can swap it back out for when you continue execution, basically. But that breakpoint's getting overwritten by our shellcode, so GDB is unable to break because, you know, it's just naively inserting a breakpoint byte there, but then that gets overwritten and confuses everything. But we can deal with that. The way we're going to deal with that is we are going to attach. How are we going to deal with that? It's kind of annoying to deal with that. We could break on print disassembly. It'd be a little bit weird. Let's do this though. Let's break here instead. And then when we break here, we'll add our other breakpoint. It's going to be slightly insane, but let's do break here, because it's going to call this function, and we're going to say these are our commands. Everything that I want you to do when you hit this location is I want you to break here, and then I want you to continue executing. So basically, once we hit print disassembly, that's when it's going to set up their breakpoint. And yeah. Okay, let's try this. Oh, and we should have added a continue in that GDB script, but we can do it ourselves. Okay, now we are broken at our shellcode. So we can see 5, 6, 7, 8, 1, 2, 3, 4. Wait, is there a bug where it doesn't sort? I think there might be a bug. That's unfortunate. Okay, hold on. Let's try one more thing. Just to see this. We add one more 5, 6, 7, 8. We do this, continue. X8i RIP 16. Okay, we can see it's sorted here. It's off by 1. It's not sorting the first 8 bytes, is it? Oh, that's so sad. We need to create an issue about that. That makes this challenge way easier, because that means you have 16 bytes to play with for shellcode. No wonder people were cheesing this solution. That makes so much more sense. Okay, so enough of this GDB stuff. We've kind of figured out what's going on here. We're not interested anymore in this. Get rid of this. So now we can at least, so it's bugged, unfortunately, but we can see that it is sorting stuff. So this is, we can send it if we send, how many bytes are we sending here? My brain is breaking. 24 bytes here. We can see that it is in fact sorting. So we have this 0, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8. So is it whatever the first, is it not sorting the first 8 bytes, or what's the off by 1 here? Nop, nop, nop. Actually, is it just not sorting this first one? Oh, what is it doing? Is it not sorting the last one? Yeah, it's not sorting the very last 8 bytes. These last, so the 0 theoretically should have been moved up to the top, but it is not being moved up to the top. Whereas, for instance, so if we did FF 1, 2, 3, 4, 0, 0, the 1, 2, 3, 4 and FF got sorted correctly, but this last chunk is just not being sorted. Unfortunate bug. I guess it makes it easier for you, but definitely something you have to, I guess, keep in mind about with solving this challenge. Okay, anyways, back to discussing more the direction of the solution of this challenge, or ways you can start approaching it. While it's bugged, there's easier ways to do it, but I'm not going to talk about that necessarily. So something you can do is, okay, so we're treating this as little endian integers. So this is a chunk. We're in TMUX, this is so sad. Do shift. This is a chunk, and then this is a chunk, right? So if we treat these as little endian integers, that means that right up front is our least significant byte. This is our most significant byte. So basically it's treating these numbers as hex 90, hex 90, hex 90, hex 00, 00, FF, FF, B8. And similarly 90, 90, 90, 00, 1, 2, 3, 4, B8. So that's basically why this 0, 1, 2, 3, 4 is ending up before this FF. Is that in terms of at the most significant byte where these two numbers are different is going to be right here. So this is where our numbers are no longer, basically everything else that's more significant, it's the same value. But right here, we have 1, 2, and then we have FF. So when we go to sort this, 1, 2 is going to end up before FF. So something you can do is, that kind of gets a little, a little clever here, is right now, if we swap around the order of everything that's just happening, so that I can get to my point a little more easily, let's swap around where these nops are and where these moves are. And in theory, everything should work the same in terms of how it gets sorted. Yep, we're going to see this 1, 2, 3, 4, and then this FF. And then unfortunately right now, this last chunk is just bugged, so we'll just ignore that. Okay, so what we have here is these 3 bytes can basically be anything right now, because what matters for sorting right now is just these 5 bytes, right? So they're not going to differ on this, they're not going to differ on this, they're not going to differ on this. Right here is where they're going to differ. So if we're inserting in this instruction, and let's pretend that we just truly do not care about the EAX register, or maybe we'll use a different register. Let's use something we're even less likely to care about. Let's say EBP. Well, we don't care about EBP. Okay, so we don't care about EBP. We can kind of pretend that these 5 bytes right here are effectively just NOP instructions. If we never care about EBP throughout our shellcode, this is just a very large NOP. It's really no different than these actual NOP bytes, but it's effectively just a large NOP. But we can make that a little bit smaller, and the reason we might want to make that a little bit smaller is because kind of the direction I'm heading in talking about this is that whatever I want these 3 bytes right here to be, they can be anything. So if we can fit our shellcode into like little 3-byte chunks, we can start like basically doing arbitrary shellcode right now, because all that matters is these 5 bytes that are being used for sorting. If instead we want to give ourselves a little bit more room than just 3 bytes to play with, let's increase this up to, let's add 2 more. Nop, nop. We'll just ignore these last 8 bytes since those are bugged anyways. And instead of EBP, let's move that into... actually, in fact, we could probably just go all the way with this. Nop, nop. And let's do 0, 1, 0, 2. And the question is, what is the least significant part of the RBP register? So BP, I can't guess it off the top of my head. Maybe it's BPL. That feels wrong. Let's try it. Oh, maybe it is. We messed something up though. How many NOPs do we have? Or I guess how long is this instruction? So this is 3 bytes long. Wait, but this is also just totally not our 0, 1, and 0, 2. 0, 2. Okay, I think it's because we're off by NOPs. Something went crazy because of this sorting, and suddenly our shellcode looks absolutely nothing like what we just sent. Seems like this is going to be 3 bytes. 1, 2, 3, 4, 5, 6. Okay, so we can't have this. So this right here, now it's going to sort a little bit more normally. Yeah. So we can see here that basically now we have these 5 bytes to play with, and then these 5 bytes to play with, and we can make them absolutely anything. So... and maybe to make things a little bit clearer, let's keep our shellcode sorted where it's at. So we have like 0x1 here, 0x2 here. That way it's not sorting it after the fact, right? Everything is just staying in order exactly as we sent it. And now if we start doing arbitrary things, like maybe we do move EAX 42, and then here we're going to do like move EAX FF, or, you know, maybe 0, 1. We can see that even though it's sorting, since we have these 5 bytes to play with and put anything we want, because the last 3 bytes are taking care of the sorting element of everything, right? And they're effectively no-op instructions, so they're not going to affect our shellcode. Kind of see how we can start to play around with the fact that it's sorting. And again, like right now we're using 3 bytes as these 3-byte NOP instructions where we can control one of the bytes to basically control sorting. So it's like a nicely sortable 3-byte NOP thing, because we control the 0, 2 and this 0, 1, which are the most significant byte of this 8-byte region. So that means this is going to be first, this is going to be second, etc. You know, hopefully you kind of see this pattern I'm talking about. Think about this a little bit more. But this is how you can start dealing with this like really strange arbitrary constraint that is like, hey, your shellcode's going to be sorted, and maybe it feels a little excessively arbitrary, but it turns out that there are in fact scenarios where you're sending some payload and that payload does have real world constraints on it. So for instance, you can imagine that you're exploiting, let's say, I don't know, the zip program, right? The zip program is doing these complex operations with compressing and decompressing data, and maybe there's some memory corruption error in there. And as part of exploiting that memory corruption, you want to, I don't know, maybe somehow you're overwriting a saved instruction pointer, which, I mean, I guess we're not talking about yet in Baby Shell, but later modules talk about that. You're overflowing the saved instruction pointer, and you really want to get it to be your value. But it turns out that you don't have the ability to just completely send arbitrary data. You have to send like a mostly valid zip file, which is compressed data. So you need to have it so that basically your saved instruction pointer that you're trying to overwrite is compressed. And you know, you can imagine these weird, then it's going to go on to decompress it and overflow the saved instruction pointer, but you have these really weird constraints. And I mean, that's kind of the idea. This does come up from time to time in the course of exploitation. Plus, hopefully, this challenge, even though it's arbitrary, helps you think a little bit more about writing assembly in more clever ways, even if the clever way is very arbitrary. Okay. So that is what I wanted to say about that level. Hopefully that helps you on your way to solving it. Turns out I did LEADIL RSP instead of move. Yeah, sometimes gotta be careful about load effective address and move and not mixing them up. Okay. Okay, so there was a question about embryo IO 93. Let's see here. Embryo IO 93. This is not the right module. This. 93. Okay. Oh boy. Okay. It kind of gets a little crazy when you're in tmux and then it re-SSHs you in and your terminal is configured in a weird way to make tmux work, and yeah, that's why that happens. Okay, challenge embryo IO level 93. What is it telling me? So it's telling me the shell process must be executing a shell script that you wrote like this, bash myscript.sh. Okay, so let's emacs myscript.sh. bash. Guess we don't really need this because we're going to invoke it with bash directly, but you know, we'll be cool here. And let's just do echo hello world. Okay. So if we do bash myscript.sh, it says, yeah, of course, it's not going to do anything. Is it want this to be coming from standard in? Wait, no. It's been a while since I've done these levels. What we probably want to be doing is we want to be running the challenge in this. Challenge embryo IO level 93. So I think it's probably checking to make sure we're launching the program from a bash script. Okay. So it now is telling us constraints. So you should have redirected a FIFO to my standard in. Checking. FIFO stands for first in, first out. True. Look at the make FIFO man page and play around with FIFOs on the command line to get a feel for them. So what that means is what we can do is man make FIFO. This is this a syscall? It sounds like a syscall. Man to make, that's not a syscall. You create a FIFO. This doesn't take, this is an unnamed FIFO. How do you create a FIFO? FIFO. Is it just a parameter to open? Man to open. FIFO. Oh wait, man FIFO. No, wait, we already Googled that. Wait, how do you create one of these? What is the syscall that does it? Wait. Man make FIFO. Syscall. You're not going to tell me this. Wait, we can just run strace. Strace make FIFO test. If we type this all correct. What did you use? What's syscall? Make node. Interesting. Did not know that was the syscall used. Oh. All right, doesn't really matter for this level, but I was curious how it is that you actually, on a syscall level, make one of these things. But don't care. But I guess we can use this opportunity now that we've created one of these things. Actually, we'll create it again. Clear. Okay, so what we can do if we want to create one of these FIFO things is we can do make FIFO and then the name of the path. So for instance, test. And now what we can do is we can do, for instance, cat test. And now it's blocked trying to send us the output of test. If we want to actually get that output, what we can do is on another terminal, we can do echo hello world to test, and that succeeds immediately. And now we can see it's done blocking, it pulled in the data. Alternatively, if nothing is reading and we do this echo hello world to test, we can see now that we're also blocked. We're waiting to send this data. Blocked until we can send this data. And now if we do cat test again, we get this data instantly, and this is finished blocking. So that's kind of the basic idea of these FIFO things, is that they're these blocking objects, basically, or blocking files. Whereas normal files will not do a block when you write to them, at least until buffers are full or whatever, but yeah. Okay, let's do, what do we want to do? Yeah, let's do bash my script. What is it asking us to do? Probably want some of these FIFO things to be our standard in. You've not redirected anything to/from this process's standard in. Okay, so if we go back to emacs myscript.sh, so we've already done make FIFO test, so that's fine. What we can do now is we can basically just redirect our standard in. So if we do this to redirect standard in, now basically the standard in of this process will be that FIFO. Bash myscript.sh. Okay, so something's blocked. And probably what's blocked is it actually going through and doing this. So if we are confused now, what we need to do basically is probably send some data to this thing to basically make it so it's unblocked, and then it's going to go through and send data this way. So let's end that real quick. Let's open up tmux so that we have more terminals to work with. And let's do bash myscript.sh. So we're currently stuck on there. If we look at all of our processes, we can see have this running. We do strace p275 sudo. We can see this is currently in bash. It's blocked on this wait syscall, so it's probably waiting for some child to finish executing. On the other hand, if we go to this other PID, so that's 275, which is probably the bash waiting for my script to end. Go to 276. We can see that it's currently blocked on trying to open this test file. So that's kind of how we can have some understanding of how things are blocked. Using strace and stuff, we're not really expecting people to use that in embryo IO, but since, we're kind of doing this backwards look at the modules in this office hours, this is kind of a way you could start understanding this. These concepts, if you're unfamiliar with, will be kind of explored a bit more in future modules though. Okay, so basically we want to send some data to this test file. So what we could do is echo hello world to test, and that's going to make it so it doesn't block here basically. And if we go back to this terminal, we can see now this finally finished executing. It actually gave us some output. So it says, good, looks like my standard in is connected to a FIFO, which is nice. Okay. You did not satisfy all the execution requirements, specifically, blah, blah, blah. Okay, so it wants a similar thing on standard out. Does it want a FIFO on standard out? There's a little bit of lack of clarity on some of these embryo IO levels, which I think does not help make them easy. It probably wants a FIFO, but let's just start with a non-FIFO. Let's just send it to hello, which is a file that does not exist yet, but bash will automatically create the file to send the data there. Okay, and then let's do this echo hello world again to test. And cat hello. Standard out is not referencing a FIFO. Okay, so we just need a FIFO again. So we'll make FIFO hello. RM hello. So we have our FIFO test. Maybe we'll just call it test2. Make FIFO test2. So now we have two FIFOs, one for standard in, one for standard out. Okay, so standard in coming from test. Standard out going to test2, two FIFOs. If we run this now, we're going to be blocked. The first thing we're blocked is on this test thing, so let's send hello world to test. And then we still don't quite have output yet. We do. Wait, what? How is that possible? Cat test2. This is a FIFO. Oh, I didn't save. Okay, save. That makes more sense. All right, run it again. We hadn't saved. Bash myscript.sh, currently blocked. First thing we're blocked in is on that standard in part. Okay, we're still blocked. Now we're probably blocked on the standard out part. Cat test2. Boom. Okay, we're close. Hopefully. Oh boy, this is where we're starting to get to the math part of things. This gets extra fun. Oh, maybe we... Please send the solution for... Okay, this is, this is getting a little tricky. Hopefully I can try and explain what's going on here along the way. It's kind of a nightmare working with all these FIFOs and interactively in TMUX and all this stuff, but I'll try to very carefully explain what is about to happen. Okay, we have this script. FIFO standard, actually, you know what, let's change it up. Let's make this a little bit clearer. Standard in, standard out. RM test2, make FIFO standard in, make FIFO standard out. Okay, so this is this. Okay. We are going to run bash my script. Okay. We are going to now do something a little bit crazy. And what we're going to do is we're going to run the cat program. The cat program, if you don't pass it anything, is basically just going to echo whatever you say. So it's going to take standard in and put it to standard out. So we'll see if we type test, it says it's test again. If we say hello, it says hello again. Basically, it's taking standard in, redirecting it to standard out. If we do cat and pipe that and redirect the output of cat to standard in, what this has done for us is that we're now talking, cat is talking to standard in, the standard in FIFO. But it's not done talking to it, right? Because cat will just continuously go until standard in gets closed. So I can start sending data to standard in. But importantly, I've opened standard in up, so we're no longer going to be blocked on, this part is no longer blocked on the fact that standard in, no one's talking to it yet. What we need to do now is standard out. So if we do another terminal, and we do cat standard out, we're now going to get a bunch of output. And we can see that cat didn't finish executing. We don't have like our $ back, right? We're still catting. It's not done. Standard out hasn't been closed yet. So basically now we have this interactive way of dealing with these FIFOs. So it says, challenge, please send the solution for 331. So it just wants us to send 331 to it. We send 331, hit enter. And now it has finished executing on our standard out terminal, and we can see pwn.college practice. So that is the idea of 93. Alternatively, if we wanted to script all of this, it gets a little trickier because we have blocking things, which means we need multiple things to start kind of happening simultaneously. In fact, it becomes a pretty big nightmare to do this in Bash. Do we want to show this? Other issues, we have to pull out. This number somehow. Probably what we're going to do is we're going to use grep to do that. Okay, let's try and do it real quick. Okay, here's what we're going to do. We're going to put this in parentheses and do an ampersand at the end, which is basically going to create a sub-interpreter within Bash and throw it in the background. So this is going to happen. It's going to be great. Then what we're going to do is, it's kind of annoying that we can't just open it. Well, we can't open it. Can't you do like open standard in? No, what is it? It's file standard in? Do we open? No, of course not file. Exec bash open file. I don't want to cat it. I want to like literally open it into the process. So we just have a file descriptor. It uses exec or something. This will open a file onto file descriptor 3. Cool. Oh boy. We now do exec 3. Let's put it on 100. And we'll do standard in. And we'll do the same thing for standard out. This is going to get really weird. So I would recommend doing the interactive way, but we're going to show how you could just fully script this. It's definitely not a natural thing to do. It is possible. Cat proc. Hold on. Let's start by analyzing what we have going on here. Proc self fd. Okay. We do Python. No, not Python. Bash, my script, sh. Okay. So we can see that on file descriptor 100, we have the standard in FIFO thing, and on 101, we have the standard out FIFO thing. Okay. Okay, cool. And then we don't really care about that. That's how we can confirm that. Then what we want to do is hat. So we want to grep this until we get this. This is like not fun. Okay, if we do like grep that proc self 101, that's our standard out thing. The reason we can't specify just standard out is because only one person's going to be opening this thing at a time. Fortunately, grep is going to be forked off from our bash process, and it's going to inherit the file descriptor. So we should be able to grep it, I think. Pretty sure. Let's see what happens if we do this. And let's do -p. Oh, we didn't do proc self fd. fd 101. What if we, instead of doing grep, do cats proc self fd 101? You can see that works. How do we need a way to basically make it so that grep won't block forever. Okay, this is going to get even crazier. Let's do timeout of 1 second of catting. We'll pipe that to grep. For this, is there more numbers? Can we keep this even simpler? Can we just grep for some numbers? Let's just grep for some numbers for now. We just grep for /d plus and do -p on that. Basically, this means we're going to read from standard out for 1 second. And then we're going to print any numbers. Oh boy. No, that's fine. Oh, that's not as cool. Four. Okay. Type that again. Grep dash O O P that. Okay, so we're just trying to isolate that number. Getting a number, cool. And ultimately where we're going to send this all to is to proc self fd 100. And then we're going to proc self fd 101. Okay, so we're going to do all of this crazy stuff. And then ultimately we're going to send that to standard in, and then we're going to cat standard out again. Okay, let's see if this works. Boom. Okay, it's pretty insane. Would 100% not recommend ever writing a bash script that looks anything like this ever, but it can be done. And that is what it would look like. Okay. Hopefully that is enough to terrify you about embryo.io. Okay, any final questions that are like kind of quick? I'm going to start wrapping up my office hours. Could you approach the 500 bash math problem, like just with bash? The issue is at some point we have math expressions that we need to evaluate, and that, well, what's the program called? It's a calculator program. Is it BC? BC. Oh god, this program is ancient and terrible to use. Would it evaluate whatever our math expressions are? Does it do like a prefix notation? No, it does 1 + 1 times 500. I assume it's following operator precedence in the same way Python does, maybe? Yeah, I mean, I guess if we really wanted to do it, we would have like this. Like do this 500 times. And we would then send it off to, hold on, we can quickly do it just for the first case. We send it off to BC to evaluate it. The issue is this /d part. We have to figure out how to cut out the prefix, but for now, let's just see. If we run this, it's going to go through BC just fine. We have to figure out how to get the whole expression now. I mean, I guess we would do like 0 to 9 plus minus divide multiply modulus. I don't know if there's anything else. We'd have to update that if there was other things. Oof, and I don't even know what is going to happen here with this dash. Do we have to like backslash a dash? Echo test grep. Yeah, I mean, I guess it would look something like this, and then you do this in a loop, and I mean, due to our timing issues, right now it'd take us 1 second per answer because of the way we're kind of getting data from here, but in theory you could do this. And I guess, yeah, you'd use BC, but it would be truly insane. Probably, if anyone's watching this and actually wants to solve embryo.io challenges, figure out how to move into Python as quickly as possible to do evaluations. Probably, I mean, maybe you prefer something other than Python, but I would highly encourage people to figure out how to get this into Python as quick as possible. That actually does the core solving. Okay, I guess I'll give you one final hint on level 11, which I don't know how generous or useless of a hint it is. But think back to levels 1 through 8 of Toddler 2. Do not forget about them on the Yawn YPU levels. They're as relevant as ever. Okay, that is all I will say for that. Yeah, don't forget about levels 1 through 8. Okay, all right, I am going to wrap up this office hours. Probably, almost certainly, my last office hours for the semester. Maybe I'll do a few office hours throughout the spring semester. Maybe there'll be interest for that. Anyways, thank you all for attending, and good work, everybody. Good luck out there. All right, see ya.